Welcome! Today, we'll explore the fascinating problem of determining whether a robot is bounded in a circle after following a sequence of movement instructions. This problem is a great exercise in understanding how directional changes and repetitive patterns can be analyzed. Let's dive right in. In this problem, we have a robot that starts at the origin, 0, 0, on a 2D plane and initially faces north. The robot can receive a sequence of instructions represented by a string called instructions. Each character in this string corresponds to a specific action. If the instruction is G, the robot moves one step forward in the direction it is currently facing. If the instruction is L, the robot turns 90 degrees to the left, or counterclockwise. If the instruction is R, the robot turns 90 degrees to the right, or clockwise. After finishing the sequence of instructions, the robot starts executing them again in a loop, repeating the sequence indefinitely. The task is to determine whether the robot's movement is bounded within a circle. This means we need to check if there exists some circle such that the robot never leaves it, no matter how many times the instructions are repeated. The output will be true if the robot is bounded in a circle, and false otherwise. Let's take a look at the first example to understand this better. Here, the input string is GGLLGG. Initially, the robot starts at the origin, facing north. The first two G instructions move the robot forward along the y-axis, taking it to the position 0, 2. Next, the two L instructions cause the robot to turn left twice. After the first turn, it is facing west, and after the second, it is facing south. The final two G instructions move the robot southward, bringing it back to the origin, 0, 0. Since the robot returns to the starting point and its movements form a closed loop, the robot's movement is bounded in a circle. Therefore, the output for this example is true. Now, consider the second example, where the input string is GG. Once again, the robot starts at the origin, facing north. It executes two G instructions, moving 2 steps forward along the y-axis to reach the position 0, 2. However, there are no turns in this sequence, so the robot continues facing north and does not return to the origin. Its movement does not form any closed loop, and the robot would keep moving further away from the starting point if the instructions were repeated. As a result, the robot is not bounded within a circle, and the output here is false. For the third example, the input is GL. The robot begins at the origin, facing north. The first instruction, G, moves the robot one step forward to the position 0, 1. The next instruction, L, makes the robot turn left, changing its direction to face west. If the sequence GL is repeated, the robot's movements trace a square-like pattern. Specifically, after 4 repetitions of GL, the robot returns to the origin, completing a closed loop. Since the robot's movement repeatedly forms this square and it returns to the starting point, the robot is bounded in a circle. Thus, the output for this example is true. Additionally, edge cases to consider include single-character inputs like G, which result in unbounded movement, or sequences like LLLL, where the robot spins in place without moving forward. Long sequences that form repeating loops, such as GLGLGLGL, also illustrate bounded movement. To determine if a robot is bounded within a circle after following a sequence of instructions, we considered several approaches. The fundamental idea is to analyze how the robot moves and changes its orientation over time. One possible solution is brute force simulation. Here, we simulate the robot's movements repeatedly based on the given instruction string. The robot executes G to move forward, L to turn left, and R to turn right. By repeating the simulation multiple times, we can observe whether the robot eventually returns to its starting point or forms a loop. Since the robot's direction changes follow a periodic pattern, we typically simulate up to 4 cycles of instructions. This allows us to determine if the robot is bounded. However, this approach has a key drawback: it is computationally expensive for large inputs, as the simulation involves repetitive calculations and a manual choice of the number of cycles. The time complexity here is n*k, where n is the length of the instruction string and k is the number of repetitions, making it less efficient than desirable. A more optimized method is to check the robot's behavior after a single cycle of instructions.
Instead of simulating multiple repetitions, we analyze the robot's final state after processing the instruction string just once.
The robot is bounded in two scenarios: if it returns to the origin, it forms a loop, or if it ends up facing a direction other than north, it will loop in subsequent cycles. To implement this, we track the robot's position on a coordinate plane using x, y, and its orientation, such as north, east, south, or west. As each instruction is processed, the position is updated for g movements, while the orientation changes for l and r turns. At the end of the cycle, we check the final position and orientation. If the position is back at 0, 0, or the orientation is not north, the robot is bounded. This approach is both efficient and clear, with a time complexity of O(n), as it processes the instruction string only once. It avoids the inefficiencies of repetitive simulation, making it an elegant solution.
Another way to approach this problem is through mathematical modeling. Here, we treat the robot's movement as a combination of vector additions and rotations.
Each movement is represented as a vector, such as north being 0, 1, and east being 1, 0. By calculating the net displacement vector after one cycle of instructions, we can determine the robot's overall movement. Additionally, the sequence of L and R instructions determines the net rotation angle. A robot is bounded if its net displacement vector is 0, meaning it returns to the origin, or if its net rotation angle is non-zero, indicating that it will rotate in a loop. While this approach is mathematically elegant and provides a deeper insight into the problem, it tends to be more complex to implement and debug. It requires careful handling of vector arithmetic and rotational logic, which can add unnecessary overhead compared to simpler methods. For these reasons, it is less practical than the optimized single-cycle check. Ultimately, the chosen strategy is the single-cycle check, as it strikes the right balance between clarity, efficiency, and correctness. The key to solving this problem lies in a few observations. First, for a robot to be bounded in a circle, it must either return to the origin or end up facing a direction other than north after completing one cycle of instructions. This is because the robot's movement pattern is inherently periodic, repeating at most every 4 cycles. Therefore, it is sufficient to analyze its behavior over a single cycle to determine boundedness. By explicitly tracking both position and orientation, we can reliably decide whether the robot is bounded. When comparing the approaches, brute force simulation is straightforward but inefficient for larger inputs, while mathematical modeling offers precision but involves unnecessary complexity. The single-cycle check stands out as the optimal approach, providing a time complexity of O(n), and requiring only constant space to track the robot's state. By leveraging the periodic nature of the robot's movements, this method eliminates redundant calculations, making it both robust and efficient. This balance of simplicity, efficiency, and correctness makes it the ideal solution for this problem. To solve the problem of determining whether a robot remains bounded in a circle, we first need to understand its movement. The robot executes a sequence of commands: G to move forward 1 unit in its current direction, L to turn 90 degrees left, and R to turn 90 degrees right. It starts at the origin, facing north. To simulate this behavior, we initialize the robot's position at 0, 0, and its direction is north. We'll use a direction array to represent the 4 cardinal directions, north, east, south, and west, as unit vectors. This setup allows us to track changes in position and direction efficiently. The next step is to iterate through the instruction string, processing each command to update the robot's state accordingly. When processing instructions, we handle each command based on its specific behavior. For G, the robot moves forward in its current direction, updating its position. For example, moving north involves incrementing the y-coordinate by 1. Turning left with L updates the direction index by subtracting 1 and taking modulo 4, ensuring it wraps around the direction array cyclically. Similarly, turning right with R adds 1 to the direction index modulo 4. After processing all instructions, we evaluate the robot's final state. If it returns to the origin, it is clearly bounded in a circle. However, if it is not at the origin, we examine its direction. If the robot is not facing north, repeating the same instructions will result in a loop, confirming that the robot is still bounded. Otherwise, it will move forward indefinitely, and the result is unbounded.
The key insight here is the use of modulo arithmetic with the direction index, which simplifies the logic for turns and avoids branching complexity.
Additionally, bounded behavior occurs in two scenarios: either the robot returns to the origin or its direction after one cycle ensures a closed loop upon repetition. On the other hand, if the robot is not at the origin and is still facing north, it will continue moving forward without restriction, resulting in unbounded behavior. To support this simulation, we use a direction array for movement calculations and variables to track the robot's position and direction. In terms of efficiency, the algorithm runs in O(n) time, where n is the length of the instruction string, and uses O(1) space since it only requires constant memory for state variables. Edge cases, such as an empty instruction string or commands that result in no net movement, need to be considered to ensure correctness.
An example input, such as GLGLGGLGL, illustrates how the algorithm works step by step.
Starting at the origin and facing north, the robot processes each command in sequence. Moving forward with G takes it to 0, 1, and turning left with L changes its orientation to west. Another G moves the robot to -1, 1, and another L turns it south. Two consecutive G commands take it to -1, 0, and then -1, -1. A left turn changes the direction to east, and a final G brings the robot to 0, -1. Another L leaves the robot facing north at its final position. The position is not the origin, and the robot is facing north, meaning it will move forward indefinitely if the instructions are repeated. Thus, the result is false, as the robot is unbounded. This example highlights the importance of checking both the robot's final position and orientation. If the robot is back at the origin or not facing north, it is guaranteed to be bounded.
To optimize the solution, we use modulo arithmetic for direction changes, avoiding complex conditionals.
Additionally, we evaluate the final state directly without simulating infinite loops, making the algorithm efficient.
The provided Python implementation follows these principles.
It initializes the robot's state, processes each instruction to update its position and direction, and checks the final conditions to determine boundedness. By adhering to these steps, the algorithm efficiently solves the problem for any instruction sequence, regardless of its length or complexity. Here, we start by defining the isRobotBounded function inside the solution class. The robot begins at the origin, so we initialize x and y to 0. It is also initially facing north, which we represent as the direction tuple 0, 1. To handle changes in direction, we create two dictionaries, left_turn and right_turn. These map the current direction to the new direction after a left or right turn, respectively. For example, if the robot is facing north 0, 1, and turns left, it will face west -1, 0. Next, we loop through each instruction in the given string. If the instruction is G, the robot moves forward by updating its position based on the current direction. For instance, if the direction is 0, 1, we increase y by 1, moving the robot one step upward. If the instruction is L, the robot turns 90 degrees to the left. We update the direction by looking it up in the left_turn dictionary. Similarly, if the instruction is R, the robot turns 90 degrees to the right, and we update the direction using the right_turn dictionary. After processing all the instructions, we determine whether the robot is bounded. The robot is considered bounded if it returns to the origin, meaning both x and y are 0, or if it does not face north 0, 1, after the sequence. This ensures the robot's path will loop within a circle. Finally, we return the result of this condition as the output of the function. Here, we begin implementing the solution to check if the robot is bounded in a circle. The robot starts at the origin, represented by coordinates 0, 0, and initially faces north. We define the direction as an array 0, 1, where the first value corresponds to movement along the x-axis and the second value corresponds to movement along the y-axis. To handle turns, we predefine two mappings, left turn and right turn. These mappings represent how the direction vector changes when the robot makes a 90-degree turn to the left or right. For example, a left turn from north changes the direction to west, represented as -1, 0. Next, we iterate over each instruction in the input string. If the instruction is G, the robot moves forward in its current direction by updating the x and y coordinates. If the instruction is L, the robot turns left by updating its direction using the next direction method and the left turn mapping.
Similarly, if the instruction is R, the direction is updated using the right turn mapping.
The loop continues processing instructions one by one, and after handling all the moves, we determine whether the robot is bounded in a circle. This happens if either the robot returns to the origin, meaning both x and y coordinates are 0, or if the robot's direction changes to anything other than facing north.
The condition in the return statement checks for these scenarios.
Additionally, the helper method next direction is implemented to compute the new direction based on the current direction and the specified turn mapping.
It iterates through the mapping and matches the current direction to find the corresponding new direction.
If no match is found, the method defaults to returning the current direction, though this case should not occur with properly defined mappings.
This completes the implementation, ensuring the robot's movement is evaluated correctly based on the given instructions. To solve this problem, we analyze the robot's movement step by step. In this example, the instructions are GGLLGG.
Initially, the robot starts at the origin 0, 0, facing north, which corresponds to the direction vector 0, 1. First, the instruction G means the robot moves forward in the current direction, so it updates its position to 0, 1. Another G moves it further north to 0, 2. Next, the instruction L indicates a left turn, which changes the direction from north 0, 1 to west -1, 0.
A second L turns the robot to face south 0, -1.
Notice how these updates are based on predefined direction mappings for left turns. With the robot now facing south 0, -1, the next instruction, G, moves it forward in this direction, updating the position to 0, 1. Another G brings it back to the origin 0, 0. At this point, the robot has completed all instructions and is back at its starting position 0, 0, but it is now facing south. Since the robot has returned to the origin, we can conclude that it is bounded in a circle. Therefore, the output for this example is true. In the next example, the instructions are GL. Once again, the robot starts at the origin 0, 0, facing north 0, 1. First, the instruction G moves it forward in the current direction, updating its position to 0, 1. Then, the instruction L makes it turn left, changing its direction from north 0, 1 to west -1, 0. At the end of the instructions, the robot's position is 0, 1, and it is facing west.
While the robot does not return to the origin immediately, the fact that it is no longer facing north indicates that the path will eventually form a loop. This guarantees that the robot is bounded in a circle. Because the robot will eventually form a circular path, the output for this example is true. Now, let's consider another set of instructions, GRGRGRG.
The robot starts at 0, 0, facing north 0, 1. First, the instruction G moves it forward to 0, 1. The next instruction, R, makes the robot turn right, changing its direction from north 0, 1 to east 1, 0. Then, another G moves it forward in this new direction, updating its position to 1, 1. After reaching 1, 1, the robot encounters another R, turning right again to face south 0, -1. A G then moves it forward in this direction, bringing it to 1, 0. The next instruction, R, turns the robot right to face west, -1, 0. Finally, the last G moves the robot forward in this direction, returning it to the origin, 0, 0. At the end of the instructions, the robot is back at its starting position, 0, 0, and facing west. Since the robot has returned to the origin, it is bounded in a circle. Thus, the output for this example is true. The time complexity of this solution is directly tied to the length of the input string, which we denote as n. The algorithm processes each character in the string exactly once using a for loop. This means we handle one of three commands, G, L, or R, in each iteration. For the G command, updating the robot's coordinates takes constant time, O1. Similarly, for L and R, updating the direction involves a dictionary lookup, which also occurs in O1 time. Since every instruction is processed in constant time and there are n instructions in total, the overall time complexity of the loop becomes O(n). Additionally, there are no nested loops or recursive calls, so the entire algorithm maintains a linear time complexity of O(n). The space complexity of this solution is determined by the amount of extra memory used beyond the input. First, the input string instructions, which has a length of n, is read-only and doesn't contribute to auxiliary space usage. Then, we have variables like x, y, and direction, which store constant-size data such as integers and a tuple. These variables require only O(1) space.
Furthermore, the predefined dictionaries left_turn and right_turn each contain just 4 key-value pairs. Since these dictionaries are static and independent of the input size, they also use O(1) space. As no additional data structures are introduced, the overall space complexity of the solution is O(1). When comparing approaches, a naive method might simulate the robot's movements by repeating the instructions string multiple times, perhaps 4 cycles, to determine whether it eventually returns to the origin. This would mean processing the string repeatedly, resulting in a time complexity of O(k*n), where k is the number of cycles simulated. However, the space complexity would remain O(1) if no new data structures are used. The optimized approach, which we use here, avoids multiple repetitions by analyzing the robot's state after a single traversal of the instructions. The robot is considered bounded if either it returns to the origin, x == 0 and y == 0, or it finishes facing a direction other than north, direction = 0, 1, which guarantees a looping trajectory in future cycles. This insight eliminates the need for unnecessary repetitions, reducing the time complexity to O(n), while maintaining the space complexity at O(1). To summarize, the proof of the algorithm's complexity reinforces its efficiency. The time complexity is O(n), because the algorithm iterates through the input string once, performing only constant time operations during each iteration. On the other hand, the space complexity is O(1), as the algorithm uses a fixed amount of memory for variables and dictionaries, regardless of the input size. This means the solution is both time-efficient and space-efficient, making it well-suited for handling large inputs while maintaining optimal performance. When tackling this problem, there are a few common mistakes to be aware of. First, many people misinterpret the concept of a circle, assuming the robot must physically trace out a perfect circular path. However, the term circle here simply refers to whether the robot's movement is bounded, meaning it either returns to its starting point or remains confined within a limited area. The actual path may look more like a square, zigzag, or another shape.
Next, it's crucial not to ignore orientation changes. While tracking the robot's position is important, the direction it's facing determines whether it will loop back or continue moving infinitely. For example, turning left or right affects whether the robot eventually aligns with its starting point. Lastly, don't forget to test edge cases. Scenarios like an empty instruction string, repetitive sequences, or movements with no turns such as GGGG can reveal gaps in your solution. These cases ensure your approach is robust enough to handle both minimal and extreme inputs effectively.
Another frequent mistake is incorrectly updating the robot's coordinates.
For example, moving north should increase the y-coordinate, but if your implementation mistakenly modifies the x-coordinate instead, it will lead to incorrect results. To avoid this, always double-check that your coordinate updates align with the intended direction. Another pitfall is overcomplicating your solution. Some people use unnecessary data structures or attempt to simulate the robot's entire path step by step, which adds extra overhead. This problem can actually be solved using constant space by simply keeping track of the robot's position and orientation. Streamlining your approach not only improves efficiency but also makes your solution easier to understand and debug. Now, let's explore some insights that can help you approach this problem more effectively during interviews. A key observation is that the robot is bounded within a circle if one of two conditions is met: either it returns to the origin after one cycle of instructions, or its orientation at the end of the cycle is not north. If the orientation changes, the robot will eventually loop back to its starting point over subsequent cycles. This leads to the broader insight that many robot-related problems revolve around analyzing movements, directions, and coordinates. Practicing modular arithmetic for position updates can help you solve these problems more efficiently. Additionally, focus on optimizing space usage. For this problem, simulating the robot's path over multiple cycles is unnecessary. You can determine the result using just one cycle with careful reasoning. While a brute force approach that repeats the instructions 4 times may feel intuitive, it's less efficient than leveraging the mathematical properties of the robot's movement. Finally, exploring related problems like robot return to origin or grid traversal challenges can deepen your understanding of similar patterns.
Let's consider some alternative approaches and their trade-offs.
The brute force simulation approach involves repeating the instructions 4 times, tracking the robot's path, and checking if it returns to the origin.
This method is straightforward and easy to implement, but it's computationally inefficient since it processes multiple cycles unnecessarily.
A more efficient strategy is single-cycle analysis, where you evaluate the robot's final position and orientation after just one cycle.
If the robot ends at the origin or its orientation changes from north, you can conclude it's bounded.
This method uses constant space and avoids unnecessary computations, though it requires a solid understanding of how to update directions. Another approach is vector-based analysis, where you represent movements as vectors and calculate the net displacement and rotational changes. While this method is conceptually elegant and mathematically rigorous, it might be harder to implement during an interview compared to simpler techniques like directional tracking. Choosing the best approach depends on the context and your familiarity with these strategies.
Great job!
To wrap up, we solved the problem of determining if a robot remains bounded in a circle. Remember, analyzing movement patterns and optimizing for time and space efficiency are key skills. Thank you for tuning in, and be sure to subscribe for more coding content.
Until next time, happy coding! That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!